to another episode of Mr. Finley doing something stupid and then relating it to maths. Now today's topic is breakfast. That's what we're going to be relating to our maths. I know a few of you have been concerned about the ever crazier titles of these YouTube videos. No, I haven't gone more crazy during lockdown. It's just given me the opportunity to talk about some slightly bizarre and crazy maths and deliver it to you guys in a lovely YouTube video. So today's episode on breakfast, we're going to focus in on two breakfast staples. Now first up is my son's favourite cereal. We're going to be thinking about Cheerios. So let's put some of those in. There we go. So we've got some Cheerios for our breakfast. And the second thing we are going to be talking about in today's episode is beans. So there we go. Actually cut that, maybe not together. That was a bad idea. So let's have a think. Cereal and beans, how on earth do they relate to maths? Now, tempting as it is, I'm not even going to get into the physics phenomenon related to these little O's. Yeah, there really is a whole lot of physics and fluid dynamics papers about the Cheerios effect, genuinely. Even a Wikipedia article. Look, they all stick together in little clumps. That is very odd, but let's not get distracted. You can go and watch a whole video explaining that. I've linked it down below. Instead of being fascinated by the physics effects of why Cheerios clump, I was instead staring at the box. And I was thinking, it's a real shame. Cheerios don't have puzzles on the back to do, which, makes them a less good children's cereal as far as I'm concerned. However, I was looking at this box and I was asking myself, does it really need to be so tall and so thin? And should it really be so narrow? Surely a wider box would be more efficient. And that got me thinking, how much packaging does it really take? And is this really the most efficient shape of box for cereal? And equally, I was looking at my tin of beans and thinking, that can't be the most efficient tin of beans that we can get. So let's do the maths. Let's find out, how close to optimal is our Cheerios box? And if it's not optimal, how much cardboard are we wasting? Let's get into a little bit of calculation. Okay, so here goes on calculating an optimal Cheerios box. Now, a few assumptions to start with. A really important one is we want to keep that nice portrait shape that a cereal box has. Now, if you, like me at breakfast, are sitting there with your ruler out and you're just thinking, I wonder what the connection between the height and the width is, you can measure pretty much any cereal box. You'll find it's around 1.5 times higher than it is wide. The other measurement, of course, is that kind of depth of the box, and so we'll call that W in this case. And so we can now write down the volume of our cereal box. So the volume of the box is the length times width times height, and in this case that's 1.5x times W, which simplifies really nicely to 1.5x squared W. What about that surface area? Well, we've got a front face, which again, we can use our measurements that we've got there. It gives us 1.5x times x, and we've got two of those, because that's the same as the back face. Well, we've got the bottom and the top of our box, which is an x times a w, and we've got two of them. And finally, we've got this face that I've highlighted in orange, and another one on the other side, and that's 1.5x times w for each of those. A little bit of simplifying. Well, that first term becomes 3x squared. Our second term becomes 2xw, and our third term becomes 3xw. Put our 2xw and our 3xw together, sort that out and get 5xw. Good, so that's our basic setup. We've got our volume, we've got our surface area written down. The other thing we're going to try and keep the same is the volume of our cereal packet. When we get our optimal box, we want it to still have 5,951 cubic centimetres of space inside it. Yep, I really did sit at breakfast and work that out. Now, a little bit of rearranging. Divide both sides there by 1.5x squared. And 5,951 divided by 1.5. Might as well simplify that to 3,967. We can now substitute in our W into our surface area equation. So let's do that. There it goes. And we can simplify. We've got some x's there that we can cancel. And we can multiply by that 5 on the top line. With this equation, we now have everything in terms of x, so we're at a point where we can differentiate to get our optimal box. But before we do that, let's move that nasty over x up as an x to the minus 1. Differentiating, 3x squared becomes 6x, and that minus 1 comes down the front, so we get minus 19,837 x to the minus 2. Bit awkward to work with, so we'll put that back over x squared because that's a lot easier to work with in a second. If we want to find our minimal surface area, we want to set our differential equal to 0, and so doing that we get that equation there, and getting rid of that take away 19,837 over x squared, we can put it on the other side. Multiplying through by x squared, and then dividing by 6 and cube rooting. So we get our optimal length for our box being 14.9 centimeters. And in fact, we can now look at the dimensions for our optimal box. Our optimal box is 14.9 centimeters long, 22.4 centimeters high, and 17.7 centimeters tall. And that gives a surface area of just under 2,000 square centimeters. Now you might see where I'm going with this. What about a real Cheerios box? Well, you might not be surprised to learn it's not entirely optimal. In fact, the actual box is nearly 2,500 square centimeters. Or to be exact, we have 452 square centimeters of wasted cardboard per box. Now that might not seem problematic. You might be like, oh, so what? But there are 139 million packets of Cheerios produced every single year. And if you put all of that waste cardboard together, it comes to over 6.28 square kilometers of cardboard. Now that's pretty hard to imagine. It's probably enough to cover Pennycook a few times over. Or, just putting it out there, it would be enough cardboard to make a single giant box where you could fit the entire Empire State Building in, not just once, not twice, but 1,000 times over. You could make a cardboard box that could fit 1,000 Empire State Buildings inside it, which is mind-blowing. So a little bit of suboptimality in box design leads to a huge amount of waste. We're going to move on to our tin can now, and we're going to see just how much waste there is in a single tin can. So here we go, let's have a look at our aluminium or tin can. And this time we've got a little animation you can see there, just reminding you where the surface area and the volume of a cylinder or a tin can shape come from. So our two key things, we have the volume, which is pi r squared, which is the area of the top times the height of the tin. And the second formula, which is our surface area, we've got 2 pi r squared for our top and our bottom. And then that 2 pi rh is our curved surface that we've got. And if you need a reminder where that comes from, just jump back, watch the animation, you'll see it again. So let's put in some numbers. Now again at breakfast, got bored, measured that a normal tin can contains about 486 centimeters cubed of volume. And we can rearrange that to get our h. So there we go, h is 486 over pi r squared. Substituting that into our surface area formula, and it looks like this. We can cancel our pi's, we can cancel an r, and finally we can do two lots of 486 and get 972 over r. We want to differentiate this in a moment, so let's write that as an r to the minus 1. Now we can differentiate, and we get 4 pi r minus 972 r to the minus 2. And putting that back into a useful form to work with, we can put that back as an over r squared. It's just always handy when you're rearranging to put negative indices back into a division or a fraction. Now, let's let that equal 0, because we're looking for that minimum point. and a little bit of rearranging later, moving that to the other side, timesing by our r squared, dividing by the 4 pi, and cube rooting gives us an optimal radius of 4.26 centimeters for a can with a volume of 486 cubic centimeters. So, you might already see where this is going already. Here's our optimal can, radius 4.26 centimeters, has a surface area of 342 centimeters squared. So what about a real can? What about the sort of can you have beans in? Well, measured one of those, turns out its radius is 3.75 centimeters, which gives us a surface area that is 6 centimeters squared bigger. Now you might well be prepared for what's coming up next. It doesn't sound like a lot having 6 extra centimeters squared per can, but when you consider that there are 180 billion cans produced worldwide every year, most of them with this kind of set of dimensions, that is a huge amount. In fact, it comes to 108 square kilometres of wasted aluminium. That would be enough to give our beautiful city of Edinburgh a lovely tin hat, or in fact, if you melted it all down and started making beams out of it, I reckon it would be enough to build about not just 1 Forth bridge, but 10 Forth bridges. That is a colossal amount of metal. As a reminder here, a little waste, repeated often enough, can be huge in terms of its impact. So why do these companies persist in being so uneconomical? Why do they persist in having suboptimal packaging? The answer is, even Google couldn't tell me. I looked it up, lots of theories to do with it being exactly what customers expect, but no one can quite decide why companies continue to churn out so much excess packaging, except perhaps that it's maybe just too cheap to do so. And one last thing before you go, maybe less of a moral point this, but before you go telling your parents that Mr. Finley's gone crazy and eats beans with his cereal, I'm maybe not the only one. The whole idea from this video? Well, it started when I was reading the Weetabix Twitter feed, as you do, and I saw that they were pouring smoothies on cereal. And, oh, there it is. Yep, that is right. Weetabix once suggested, on the 9th of February this year, that maybe it would be fun to have beans in your Weetabix. I'm still not convinced, but possibly better than Marmite.